Thanks very much for the invitation. This really looks like a placeholding title, right? It looks like, oh, we didn't know what Dan was going to talk about, so we'll just give this title here. And it should really be, if that was a placeholding title, it should be or planetary interiors, because it's really too much to talk about in one talk. So, but if we're interested in what the structure of planetary interiors might be and how the dynamics of other planets might be, then what we're really interested in is some of the major element compositions of the different planets. So some of the things we might be interested in is how big is the core, for example, in relation to the mantle of a planet, how much iron oxide is in the mantle. That certainly will determine a lot of the phase relations of the mineralogy of the mantle's interior. What's the magnesium-silicon ratio of the mantle? So if we knew what the FeO concentration and magnesium-silicon ratios of a particular planet's mantle were, we could make a pretty good estimate for the structure, the mineralogy of that planet. And another thing we might be interested in would be perhaps how much heat-producing elements have been accreted to it, but also perhaps how much volatiles are in there. So, for example, how much water might have been accreted to that particular planet. Certainly for plate tectonics, that might be very important. Water appears to have a big effect on the viscosity of mantle minerals, so a knowledge of how much water might have accreted to different planets might be quite useful. But so what I'm really going to talk about are models for the accretion of planets. And these have really been developed to explain the chemical composition of the Earth's mantle. But in principle, those models can be applied to then understand what the composition of other planets should be. And I don't really want to get too geochemical on everybody, but this is, I'm certainly not going to talk about isotopes, that's at least one thing. But if we look, what this is showing is the concentration of elements in the Earth's mantle today, normalized against C1 chondrite. And C1 chondrite is a type of meteorites that we think the Earth may well have accreted out of. And then this is plotted against what we call the 50% condensation temperature. So that's the temperature when you condense out of the solar nebula, where 50% of that element would have appeared. So if we look at these concentrations, so if we have a C1, a meteorite concentration in the mantle, then it should plot around 1. And we see a lot of these, what we call refractory lithophile elements which condense at high temperature and don't partition into the Earth's core, are still in the Earth's mantle in these C1 ratios. And this is one of the founding principles of geochemistry, that the Earth seems to have accreted from a type of carbonaceous chondrite. But then if we look, we've also got lots of other elements which are depleted. Some of these are clearly depleted as a result of volatile behavior, so some processes influence their volatility, but many of them are also depleted as a result of siderophile behavior, and that means that they partitioned into the Earth's core during the core mantle differentiation process that happened during accretion. And really, a lot of geochemical models, and in Bayreuth we developed models, and many other people in parallel, we develop a geochemical model to try and understand these depletions in the Earth's interior, in these mantles. And most of those models are purely based on the geochemistry and trying to reproduce the geochemistry of the Earth's mantle. But implicit in those geochemical models are physical scenarios. So scenarios, dynamic scenarios of astrophysical collisional accretion of planets, and also the fluid dynamic processes of core mantle equilibration. So it's not really just a geochemical problem. There should be a lot of constraints that we can apply to this, to the geochemical issues, by looking also at physical models for the dynamic processes that occurred during accretion. And that's what I want to try and talk about, is combining the partitioning and geochemistry of mantle differentiation with dynamic models to place constraints on the accretional processes. And really, one of the only few pieces of information that we have about how accretion occurred is this geochemical depletion of the Earth's mantle. So it really provides one of the few tests, aside from a few orbital parameters, on how the accretional process during the formation of the solar system actually operated. So purely for testing the dynamical models, it would be correct to combine those dynamic models with geochemical partitioning to understand the resulting depletions of siderophile elements in the Earth's mantle. So given that this is some of the only evidence that we have, it's important to try and exploit this to the best of its possibility. Now, what I'm going to show is the way that we try and combine these dynamic models with geochemical partitioning, and we're not really trying to completely reproduce the accretion of the Earth and the separation of the core. We can't hope to really reproduce such a dynamic and stochastic process, but what we hope is to provide some robust indicators for the ranges of conditions and processes that may have been possible. So, just briefly, just go back to this diagram. There's a lot of problems in the Earth which have been recognized in the Earth's concentration of mantle siderophile elements. So certain elements like nickel and cobalt, for example, are present in the mantle in their chondritic ratios, but actually if we just look at their one-bar partition coefficients, they should be fractionated from one another, and there should be much less nickel in the mantle. And the same goes for highly siderophile elements. And it doesn't look as if these processes, of these fractionation events, could have happened at what we call the same redox conditions. And when I'm talking about redox conditions, it's really just a I wouldn't say a metaphor, but we can really understand redox conditions by just considering how much iron oxide was in the Earth's mantle. So if vanadium looks as if it's gone into the core, and when vanadium went into the core, you'd really expect there to have been very little FeO in the Earth's mantle, so quite reducing conditions. Whereas to deplete nickel and cobalt to this level, you would expect less reducing conditions, more oxidizing conditions, more FeO in the Earth's mantle, and for highly siderophiles to be in these abundances in the Earth's mantle, you expect really oxidizing conditions. So it doesn't look as if all of these siderophile elements, all of their concentrations were developed at the same conditions. It looks like there was a series of processes. And if we trace back the history of basically geochemical models to explain these distribution of siderophile elements, then one of the first all-encompassing models for the formation of the Earth, based on trying to understand this geochemistry, was from Hugh O'Neill. And he came up with this. Hugh O'Neill first accreted the Earth, and he did it in his office in Bayreuth. Yeah, so this is my institution. We now keep that office as a shrine. It's where the first accretion of the Earth took place. The model that he came up with is there to explain these different depletions of siderophile elements. And as a result of the reasoning, he came up with quite a complicated model. First of all, you have a reducing phase of core formation where there's very little iron oxide in the Earth's mantle, and all the metal goes into the core, and it completely extracts all the siderophile elements. This is followed by a more oxidizing stage of core formation, which he associated with the moon-forming impact. This puts FeO-rich material and just accretes the entire mantle with very little core formation taking place. But then he realized that he had this problem with highly siderophile elements, that you would have too many of them. So then he had to create a sulfur-rich liquid which takes these siderophile elements out of the core, out of the mantle rather, and brings them to the core, and he called this the Hadean mat. And then, finally, to establish the highly siderophile element ratios in the mantle, he has to then accrete a late veneer. So a late veneer of oxidized material, about 1%, which then doesn't have any core formation and brings our highly siderophile element abundances. Trouble is with these models, and people said that at the time, is that they're really pretty complicated and pretty untestable in many ways. It requires an act of faith, in fact, one might say. So, but then a few years later, people started doing high pressure and temperature experiments to try and understand how these siderophile element ratios might have developed. And Leonagi and Reiter and Drake did these experiments where they recognized that the overabundance of nickel in the mantle could simply be explained by high pressure and temperature equilibration. So if we have a deep magma ocean, so they argued for a magma ocean on Earth about 700 kilometers deep, and all core formation occurred at the base of this magma ocean, so droplets dropped to the bottom, they equilibrated, and then they separated to the core. And if you do the partitioning of the siderophile elements at this high pressure and temperature, you find that you get the right chondritic ratio of nickel and cobalt, and you get the right depletion of both of them from the Earth's mantle. So this seemed to avoid having to have more complicated models. This was nice and simple. They said, okay, the whole of the Earth was formed as a result of a magma ocean forming with one depth, 700 kilometers depth, at one pressure and temperature, and one oxygen fugacity. So this is a totally homogeneous accretion model, a single composition, single redox state, a single pressure and temperature. And of course, by looking at many different element ratios, you can provide some excellent constraints on this one set of conditions. And given that that is perhaps one of the simplest explanations, then many of these people then argue that it's heresy to even think about any more complicated models. However, people do. So Wade and Wood, a few years later, they said, well, it's pretty unlikely that core formation happened at a single pressure and temperature. Because we know if we look at iron meteorites, these are from bodies which are only a few hundred kilometers in size, and they're already differentiated. So it's pretty likely that core formation, core mantle equilibration, was taking place even on relatively small bodies, and that the Earth's mantle compositions probably reflects a more polybaric equilibration process, where as the Earth grew, metal was being separated continuously, and you would expect metal and silicate partitioning to have occurred over a range of pressures. And they, in fact, solved the same problem. They matched the composition of the Earth's mantle using a model where they actually changed the pressure and temperature during the growth of the Earth. But then, to actually fit all of the elements that they wanted to fit into this model, they had to loosen the constraints a bit furthermore. They had to say, well, actually, we get a better fit when we start off with reduced material, so with very little FeO in the material that was accreting to the Earth, and later on it evolved to become more oxidizing. So again, after a phase of high pressure core formation, people started to move back towards ideas that the material that was accreting changed in oxygen fugacity from initially more reduced to eventually more oxidizing. And that's very similar, of course, to what Hugh Neal had initially proposed. And then just to make sure we get a good balance here, last year, Sibert and co-workers, they came up with a similar but opposite idea. So they argued that you could explain the mantle abundances of all these siderophile elements if you actually started off with a more oxidizing material to begin with, and you got more reduced with time. And they argued that this results from oxygen dissolving into the Earth's mantle, which then reduces the oxygen fugacity of the process. And there again, you start to see with this idea that you can change the oxygen fugacity of these processes not by appealing for material changing in composition from space, but simply by putting an element like oxygen into the Earth's core. So simply by partitioning in the light element, we can already change this oxygen fugacity process, because we then create more iron oxide, which then goes into the mantle. However, these are all geochemical ideas, right? They're all models just purely based on geochemistry. Implicit in them are physical processes, dynamical processes, such as the accretion of the planet. And surely it should be possible to provide more constraints by incorporating these dynamic processes into such core formation scenarios. So these are what we call n-body simulations. They're dynamic simulations. This is nothing to do with us. This is performed by people like Alessandro Morbidelli and O'Brien. And what they do is they start off with a series of planetesimals and embryos in orbit, and then they allow their mutual gravitational attraction to influence the way that those orbits interact with one another. And it throws material up into more eccentric orbits, which ultimately leads to collisional growth of the planet. So starting off from a number of particles, and they start off with what they call both embryos and also planetesimals, in the end they end up with this process where you start forming a series of planets. So this should also provide some sort of constraints on this process, particularly when we think that at the beginning what you see in the simulation is that we've colored these particles to reflect the different original position where these particles formed. But then during this chaotic process, there's a lot of mixing that then goes on in these models. And now there are a large number of these models. And of course, we could try to test these models to see what sort of planets you really formed as a result of these types of simulations. And there are many other simulations, such as the Grand TAC model now, which I'm not going to go into, but that involves the motion of Jupiter, first inwards and then outwards into the solar system. And what that does is it truncates this disk of planetesimals to begin with, and it ends up with producing Marses which look a bit more like Mars. So this is one of the points from these simulations, that of course very rarely do we actually come up out of one of these simulations with planets that look like the planets we have. Here is probably one of the best simulations that they've produced, and you can see this is pretty reasonable, but the Mercury that is produced is a little bit large. So the first thing that we would then try and do is try and understand what this might mean, what these initial source region distances might mean for the composition of the material which is then going on to accrete the planets. So if we look at any meteorite, chondritic meteorites, for example, not C1 meteorites, but we then normalize the composition of a C1 of a meteorite to C1, we see that relative to C1 chondrites, which is the material we think probably most of the planets are formed out of, most of the terrestrial planets are formed from, relative to C1, all meteorites show depletions in volatile elements. Right? So as we go to elements which condense at lower and lower temperatures from the solar nebula, there's an increasing depletion in any chondrites except relative to C1. And if we look at the Earth, and we just look at the lithophile elements that probably haven't gone into the core, we see that the Earth looks very much like a chondritic meteorite, not C1, because it has these depletions in volatile elements. And the principal model that people argue for explaining this depletion in volatile elements is a result of condensation. That initially, we had the sun and there was a gradient in temperature away from the sun, and condensation took place from that solar nebula inside that thermal gradient, such that condensation only proceeded down to the levels where we would condense ices out at, further away from the sun, but closer to the sun where temperatures were very high, we would have only have condensed material down to produce silicate minerals and some iron metal, for example. Now the point is that at some point the sun went through a phase where it blew away the solar nebula, and what was left was then material which had a gradation in the level at which it had condensed. And we know from a first look at the solar system that something like that pretty much must have happened, because we have an inner solar system which is completely very much devoid of much of the solar nebula, and an outer solar system where we have gas giants that have compositions similar to the solar nebula. So if we look, we do what they call condensation models. Using a gradient for what we expect for the initial disk, we can go down and model at what temperatures we expect different minerals and different elements to have condensed, getting all the way down to water. So this would give us some idea of what we expect for the gradation of volatile elements. But the thing is that when we create FeO, when we condense and we make FeO, FeO is also what we might think of as a volatile element, because the main way you make FeO out of the solar nebula is you react iron with water to make iron oxide and hydrogen. And this process only actually happens once we get down to relatively low temperatures. So we expect, actually, along with this volatility, we also expect a gradation in the way that we have FeO in the condensing out of the solar nebula. So, and here is a model. This is what we'll ultimately use. I'm not going to use this at first, but what we'll ultimately use for such a gradation in terms of both the volatile concentration and the redox state of material with heliocentric distance. So this is our attempt at trying to reproduce what we expect for the initial compositions of those planetesimals before they go through this collisional growth phase. And we start off with material which is highly reduced, which of course that looks, some meteorites like Ensitite chondrites really do reflect this high level of reduction. And we go away from the sun and we get more oxidized and also more volatile rich material as we move away. So what I'm going to try and show you now is some modeling where we've really combined these particle simulations. So we track each one of these little collisions from this initial chemical composition, and we grow the planets, and then at each collision we then calculate how elements would have partitioned between the mantle and the core as those planets go through this phase of growth. And of course, as the planets are growing, the particles and the embryos which are actually colliding with the Earth are also, some of them are also growing in size, but not always. That's a stochastic process. It's a chaotic process in many ways, and it's reflected by, in many ways, the starting conditions of these simulations. But of course, you can put hundreds of simulations through and get some idea of the statistics. So then what we do is, after each collision, we then calculate the compositions of the Earth mantle and also of the metallic liquid, and then we maintain a mass balance between the compositions which are making the silicate mantle and the compositions of the core. So we don't actually assign an oxygen fugacity to this process. We don't say this happens at this oxygen fugacity. we calculate what the oxygen fugacity is as a result that's completely constrained by the material which is accreting at that moment. And also, it's affected by the elements which are partitioning into the Earth's core. So here's one other aspect of dynamic simulations. I mean, we don't do these simulations, but we look through the literature and we find dynamicists, numerical modelers who are actually doing simulations of these magma oceans, and it seems relatively pointless for them to have done these simulations if we don't try and incorporate their results into some sorts of models for the chemistry. So here's something else which we thought was unrealistic. So in the original geochemical models, it's just assumed that all of the metal which is being accreted to the Earth is equilibrating with the entire Earth's mantle. And that's just assumed by geochemists, that you equilibrate the metal with the entire Earth's mantle during one of these accretion phases. But some fluid dynamic experiments and also calculations seem to indicate that this probably isn't the case. What happens is that as you accrete planetary bodies, the silicates do mix with the mantle, but the cores, although they might break up into droplets, depending on the size, this is not necessarily the case, but they then start to entrain. As they drop towards the core, they create this magma ocean, and they entrain inside that magma, inside that material, they entrain silicate material, and what descends is a descending plume. I'm not sure what's the word for a descending plume. Can you say that? Okay. So plume, by the word plume, it's not implicit that it's going upwards, is it? Is there a word for a plume that's going in the other direction? No? Okay. Just thought I'd check there that I'm not sort of breaking some dynamic kind of like a... Okay, so we should make a word for that, actually. This is just a mixture of the metal and silicate, but the region in which this, with this reaction, this equilibration is taking place, is actually controlled by some calculations that they propose in this paper, and we can incorporate that sort of thing also into the simulation. Now, of course, it's not possible for us to exactly reproduce the conditions of each one of these events, but by playing around with these types of simulations, we can see what's possible and what the implications are. So what that means is that in each accretion event, you only equilibrate the metal with actually a relatively small part of the silicate mantle, and it's that equilibration with the mantle that is picked up in the chemistry of the Earth. But what that also means is that incorporating these simulations into core formation means that you drive the pressures of core mantle equilibration to higher pressures. That's what we find within these simulations. So it means that high pressures probably had a lot to do with these with the equilibration conditions. Now let me just show some experiments. So this is all then based on the way we form the core is based on doing high pressure and temperature experiments, and Jamie Badrow and his group and we've been for many years doing these types of experiments. And I really mainly do multi-annual experiments most of the time. I try and heat these things up at pressures of the lower mantle, but we can only really get to pressures of about 25 gigapascals, so about 700 kilometers. And it's probably no coincidence that most of the people who use the multi-anvil then argued that the base of the magma ocean was about the limit of the multi-anvil device. But now many co-workers, many other workers have also done these very high pressure experiments in diamond anvil cell. And as a multi-anvil person, I was always skeptical about how you can control diamond anvil cell experiments. But when you look at the results of Jamie's group, and then these are some experiments that we've done in collaboration with Rebecca Fisher, and you then cut sections out of these samples using a focused ion beam, and then you can analyze them on the TEM. So this is a metal blob, a core here, which is about 5 microns across, and around the outside is our molten silicate, our magma ocean, and here you can even see the solid silicates around the outside. And actually, I have to say that these experiments are looking better than our multi-anvil experiments. And the multi-anvil for me was always the benchmark of good experiments, but really it seems to be possible now to get just as good results in the laser-heated diamond anvil cell, which is important because we think that pressures of equilibration very well went up to pressures towards the end that was at hundreds of gigapascals. So I'll just make this point, that rather than the oxygen fugacity being necessarily constrained by some outward process, by incorporating these dynamic processes, we can simply constrain the oxygen fugacity from the composition of the material and by tracking the amounts of light elements which are going into the core. And this is very important because when iron, when silicon goes into the Earth's core, it releases FeO that goes into the mantle. So that raises the oxygen fugacity of the mantle. So putting silicon into the core raises the oxygen fugacity. So by tracking this mass balance process, or mass balancing this process, we get some idea about how the oxygen fugacity evolves and how the iron oxide concentration of the mantle evolves. And you can see here that as we go to higher and higher pressures, we get silicon and oxygen going into the core, and that alone has an influence on the iron oxide concentration of the mantle. So this isn't the FeO concentration of the mantle here is not going up because material's coming in that has more FeO in it. It's simply going up because we're putting silicon in the core and making FeO, which goes then into the mantle. So these are images of a grand tack simulation. So within one of these simulations, within one of these n-body simulations where we accrete all the different planets, in this simulation we were successful in making all 4 planets, and you can see that in each stage, in each one of these stages, we then have an impactor which we equilibrate with the core, and we try and make the planets at the end of it. And this simulation was reasonable. It made a Mars, it made a Mercury. Mercury's, like I say, a little bit too big, but nonetheless, we could track how these simulations operate. Now, one thing I want to say is that before I talked about our perception that probably there was a gradient both in the volatile concentration and in the redox state of material before accretion. And we can test this now in our models by assuming for a moment that actually there was no gradient. So we can check now what happens if we have a homogeneous accretion model. And of course, with all these simulations, once you have the program, it's easy just to flip in lots of different starting compositions and accrete planets, and it comes out in seconds through these simulations. It's not a problem. So we can test lots and lots of different compositions, and this was our best fit for a homogeneous model, and here is a fit for a more oxidizing model, for example. And what we find is that once we incorporate these dynamic simulations together, we don't find a solution with a homogeneous accretion model for the Earth. We can't actually reproduce the Earth's composition. In the end, that's reproduced here by these little boxes. We're accreting the Earth, and the chemical composition of the mantle is changing, and we're tracking that chemical composition. But you see many of these don't end up in the right bounds, and we weren't able to find a homogeneous model where we could sufficiently accrete the Earth. Even starting at very oxidizing conditions, one of the things is that you always end up with some silicon going into the core, whatever conditions at very high pressures, and that silicon then puts iron oxide into the mantle, and although that oxygen partitions between the mantle and core, it still doesn't stop here, for example, the iron oxide concentration of the mantle going down. So we tried and we put lots of different simulations in, but we weren't able to find a homogeneous model. So the simulations which I'll show now go back to a gradient in the oxygen fugacity, which would be consistent with a lot of condensation models. So what I show here now are results from these grand tack models from Alessandro Morbidelli. So these are the results of these collisional growth of planets. And here's this initial distance away from the sun. And what you see at the end is how much of all the different material is incorporated in the planet. Now, one embarrassing aspect of these particular 6 simulations, which is all that we have that make 2 good Earths, which make an Earth and a Venus, is that they don't actually accrete a Mercury, which is in some ways a bit embarrassing. And the Mars is a bit all over the place. Well, okay, what can we say? So one other point is to do with water. So it's always interesting to think how water would be accreted to other planets. And the thing with a metal silicate equilibration is that as you put metal into a silicate magma ocean, you should basically reduce water and create hydrogen, and that hydrogen should either disappear from the Earth or go into the core. So it's very difficult to actually put water into the mantle normally with a normal geochemical type model without actually reducing it to hydrogen. So that meant that lots of geochemists have argued that the water must have arrived after core formation had finished. So basically in this late veneer. And the problem is that the late veneer ends up being quite well constrained by the amount of highly cytophile elements, and there's not much of it. And what it means is that you have to accrete a very water-rich late veneer to match to give you enough water in the Earth. But one of the outcomes of these models is that what we find is that when you track this core-forming material, not all of this, because the core-forming material only interacts with a small amount of the mantle, you can start to accrete oxidized and water-rich material to the Earth which actually does never interact with iron metal. It's only a small component of it, but it's actually enough to accrete the Earth's water without having to wait for a late veneer. And I can show you that in these models now. So these are various models using these Grand Tack models by Alessandro Morbidelli and tracking then the composition of the Earth's mantle as a result of these accretion processes. And you find that, of course, these are all very different compositions because the material accreting the Earth at any one time will vary depending on the particular simulation. But what you see is that initially, water-bearing material does indeed get reduced by this process, but we have internal regions of oxidation in the mantle which allow enough water to be stored. And in various of these models, we actually end up with a reasonable water concentration for the Earth's mantle, even without having to bring that in a late veneer. And that's simply because some of the mantle that's being accreted is never actually equilibrating with iron metal. A small part, but enough to allow the iron metal to not reduce all the water. So these are now results for Venus. I've blanked out all the trace. Oh, can you? 30 minutes. I'm done. Okay, I'm doing it. Well, that's all right, because this is about the second to last slide. So, okay. I thought you said you have 30 minutes. Now I'm wasting time. Sorry. So these are results for Venus, and so these are 6 different Grand Tack models, and actually they refine the FeO concentration of the Venus mantle. I mean, this is now predictive. We're constraining the results of the model to fit the Earth's mantle, but then we're accreting Venus at the same time. So now we can look at the composition of the Venusian mantle. And the FeO concentration is in general slightly lower than the Earth's mantle, which would actually seem to fit. And we get the silica concentration, which is also in agreement, and we get a very similar water concentration. And when we look at the light elements that we get in the core, they're dominated by silicon, but also with some oxygen. And then when we look at Mars, like I said, in these Grand Tack simulations, is a little bit chaotic. Sometimes we make a Mars that's too far in, and sometimes we make one that's too far out. And when Mars is far enough out, actually we get a composition for the Martian mantle which is pretty close to what people estimate for the composition of the Martian mantle. But actually in this particular simulation it doesn't end up with any water in it because it actually interacted with enough metal that we lost all the water. The point about Mars is that because Mars is small, it can be dominated by the impact of just a few planetesimals. So if you have just some planetesimals which are particularly large, they totally dominate the way that you accrete Mars. So one last point now. So when we look at the accretion of these planets, we are putting light elements into the core. And as the planets get larger, the energetics of the accretion process is higher, the planets are larger, so the bottom of the magma oceans is much deeper, and we start to put more and more light elements into the core. So actually at the beginning of core formation, if this is the core, so this is the center of the core, and this is as we go further away from the center of the core, and this is the amount of iron. So early on during accretion, the iron that you're making of the core is pretty much iron metal with a bit of nickel and very little light elements. But as we get to higher and higher pressures of accretion, we start to develop more and more light elements in the core. Now, of course, these are light elements which are arriving at the core. They don't really have much of a propensity to then mix with the core because they're actually light. So one of the ideas that we're working on is that you end up at the end of a normal accretion process with a stratified core with a lot of light elements sitting on the top of the core. And maybe this is a problem for starting the dynamo, but perhaps a late giant impact can actually help to then mix this material in and start up the geodynamo. And perhaps if we look at Venus would have had exactly the same stratified mantle, but perhaps on Venus it doesn't seem to be that there was such a late giant impact on Venus. Perhaps this didn't matter. This didn't happen. So in effect, the impact of a Mars-sized impactor would then instigate the mixing of the core and then start the geodynamo. And I was thinking about this just on the aeroplane last night. I was thinking, well, we could start Venus's dynamo by impacting it with a Mars-sized impactor, because we do have another Mars left over, don't we? I mean, there's one left, so we could try that somehow. Okay, so in summary, yeah, maybe I've gone on too long, but we combine these n-body solution models to try and get some constraints on what really the n-body accretion models would mean for the chemistry of planets. And it seems that we can accrete water very, very early. We seem to find that we have mantles, cores which are dominated both for the Earth and Venus with about silicon and some oxygen. And perhaps what happens is that towards the end of core formation, we develop this light element stratification on top of the core. Thanks very much.
Thank you.